Now let's consider a uniform cross-section. So for example, now you have a bar. It has a rectangular cross-section. And for this rectangular bar, there is a cross-sectional area A, and its cross-section is uniform. You apply the load P on the two ends. So the behavior of the bar in the solid mechanics will be rather similar to the behavior of a spring. What does that mean? When you stretch a spring by using the load P, the spring will become longer, and when you compress the spring, then the spring will become shorter, right? So this is what we are dealing with actually. We consider the material as the linearly elastic. That means like the spring. So we know that for spring, when you apply the P force, then you will get F equals to minus Kx. Still remember that? So it is similar, it is quite similar in solid mechanics. Okay, so we consider there will be a constant that is linearly related to the distance and the force. So only thing is that we change the notation from F to P, and we will change the notation of the stress a little bit, because in this course we consider two kinds of stress. One is the direct stress, one is the shear stress, which is to be introduced to you later on. So for the direct stress, it is called sigma. Sigma is defined as the force acting on this area, and we assume it is uniformly distributed. So this is the distribution. Then the direct stress will be, of course, similar definition. The force divided by the area. And notice that it has the unit of Newton per meter square. So you know that the force has a unit of Newton, area has a unit of meter square, then the unit will be consequently Newton per meter square. And those formulas can be very similar to what we just introduced. So you know the force is the area integral of the pressure distribution. And very similar for a spring, when you have a tensile load P acting on the tip, it will become longer. If instead you have a compressive P, then the spring will become shorter. So rather similar to the spring, when you apply a compressive load, we treat this load to be negative, and the delta is a deformation of the material. So back to the solid mechanics, we have a bar. In case we have a compressive load P, then the bar will become slightly shorter, and there will be a deformation. So for the deformation, you know that it is relevant to the force, and in this course we define that in case you apply a compressive force, that means you will make the deformation negative. That means in case the deformation is negative, the bar is shortened. And similarly, in case you apply a tensile load P, then the bar will become slightly longer, and the delta will become positive because the bar has been elongated, and consequently we will treat this tensile load as positive. It is rather similar to what we have learned in statics and dynamics. So as you can see, when you apply a load P, there will be a deformation. Notice that the deformation can be either positive or negative, depends on your P. So in case your P is pointing back, then your beam will become shorter, then maybe this part will become shorter. And notice that, of course, the deformation is very often not that big, so it is just an enlarged view. So actually, in our daily life, the deformation of the material is very, very small, maybe. So we know that the normal stress is given by P divided by A. We will define some quantities in order to proceed. So we will define the axial strain. What is axial strain? It is called epsilon. So epsilon equals to delta divided by L naught, where L naught is the original length of the material under no load. When in case there is no load applied, the original length is L naught. So epsilon is just the amount of deformation divided by the original length L naught. And in case we assume this material is linearly elastic, there will be some quantity like K, right? Because we know F equals to minus Kx for springs, right? But for solid mechanics, instead of using K, we will use E. Okay, so we have a material property E, varies with materials. This property is called Young's modulus, so you might have heard it in Physics 1112. And now introduce the Hooke's law for axial stress and strain. So Hooke's law, you have heard it for a lot of time. For springs, it is F equals to minus Kx. But now we just try to use it to be something in the solid mechanics. It means that the normal stress, so the unit of stress is Newton per meter square, okay? So it equals to Young's modulus times epsilon. So notice that what is the unit of epsilon? Epsilon equals to delta divided by L0. So the unit of delta is meter, is the length, right? L naught, the unit is also length. Length divided by length means no unit, means it is 1. So the unit of Young's modulus will be Newton per meter square as well. So Hooke's law of axial stress and strain means that the axial stress equals to the strain times the Young's modulus. Notice that the larger strain means larger deformation. Consider the definition of the strain. The larger stress developed in the cross-section of the material. Harder material has harder Young's modulus. So just now we have already discussed the units of Young's modulus. So to emphasize, the unit of Young's modulus is just the same to that of the pressure or the stress. And also, by using all those three formulas, we can derive the deformation of the material under load P. So delta, we will rewrite this one to be delta equals to epsilon L naught. And we substitute the Hooke's law and make the epsilon to be the subject. Then it will become sigma divided by E times L naught. And at the same time, we keep those two here, okay? And we write sigma equals to P divided by A here. And eventually, you can have this formula. So it is the deformation of a linearly elastic material. So in case the original length, the L naught is L, then the formula will become delta equals to PL divided by EA. Well, how can we remember this formula? I believe all of you have taken ALPA exam, right? So it is just ELPA ALPA, English Language Proficiency Assessment, right? So delta equals to ALPA. Okay, remember PL divided by EA. ALPA. No ALPA. ALPA, okay? ELPA ALPA. I don't want ALPA, right? So all those formulas are only applicable for ball with uniform cross-section. As an important reminder, P can be either positive or negative. That means the deformation can be either positive or negative. Okay, so the beam can be elongated or shortened, depends on the loading conditions. So how about non-uniform cross-sections? So we know in this world we are not always dealing with wonderful conditions. We need to deal with some real situations.